So today I'm going to talk about partial derivatives. This is a topic that I see a lot of students struggle with, but using a handy trick, these problems become a lot easier to solve. So let's talk a little bit about what a partial derivative is before we learn how to solve one. A partial derivative is very similar to a regular derivative with one major exception. The original function that we use for partial derivatives is going to have multiple variables. The functions that you've been used to seeing probably only used one variable up until this point. So everything was in terms of x or y, or maybe t if the problem was talking about time. But now we're going to see slightly more complex functions that have more than one variable in them. Here you see a few examples of functions with just one variable, and then some functions with more than one variable. When we're dealing with the one variable functions, taking the derivative is very straightforward. But when we're dealing with more than one variable, then we run into an issue. How do we handle multiple variables? We think of a derivative as the slope of a line, but if we have a function of multiple variables, we aren't dealing with a line. We're dealing with a plane if we have two variables, or a three-dimensional shape if we have three variables, four dimensions for four variables, and so on. So it's not really easy to think of the slope of a three-dimensional object. But the good news is we don't need to visualize these types of problems in order to solve them. What we need to do is make these multiple variable problems into just one variable problems. And the way that we do that is by holding the other variables constant and taking the partial derivative with respect to just one variable. So let's see how that's done. So the first thing that we want to do when we see a multiple variable function is figure out how many partial derivatives we will have. This is pretty straightforward because we're going to have a partial derivative with respect to each variable. So for the two variable case that we see here, that means that we'll have two partial derivatives, one with respect to x and the other with respect to y. And we write those like you see here. The funny D-shaped symbol is just the symbol for partial derivative instead of the prime notation that we use with regular derivatives. On the top, we'll have that cursive D symbol and the function that we're interested in, and on the bottom, we'll have the symbol again, but with the variable that we're interested in. And the notation here is really crucial because the variable on the bottom here tells you which variable is going to be treated like a variable. The other variable, or variables if you have multiple, are going to be treated as constants. So let's see how we'll do that. Let's start with the partial derivative with respect to x. This notation means that we're going to take the derivative of this function when x is allowed to vary, but y is held constant. So even though it looks like a variable, we're going to treat y as a constant. So the first thing that I'm going to do here is rewrite the function with a box around each of the y's and any exponents or natural logs that are attached to the y's. This is because if we're treating y as a constant squared is still a constant, and the natural log of a constant is still a constant. So the box reminds us that, again, we're not treating y as a variable. We'll talk about natural logs within partial derivatives in a separate video, but for now, we're just going to stick to exponents. Here we see all of the y's, and the exponent that's attached to the second y, are now within boxes. This function is still a rewritten version of our original function. We haven't actually started taking the derivative yet. So now we're going to do that. We're going to take the derivative of each piece outside the box and then multiply back in the boxes. The reason why we can do this is because of the constant multiple rule. Everything that is within a box we're treating as a constant, which means that just like any other constant, we can take the derivative first and then go back in and multiply back in the constants. Each of the arrows is where we've taken the derivative. So the derivative of 3x squared is 6x, the derivative of 2 is 0, and the derivative of 3x is just 3. Notice that we've kept the addition and subtraction signs exactly the same as before. So now it's time to multiply the boxes back in. The blue arrows show how the boxes have been multiplied back into the function. Remember that these are constant multiples, so we can't just ignore them, but this method allows us to deal with the easier derivatives first and then come back and deal with the constant multiples. In the last step, we simplify this new function. So 6x times y just becomes 6xy. The 0 multiplied by the y cubed becomes 0 because 0 multiplied by anything is just 0. And the 3 is left untouched because there were no boxes in that piece to begin with. So here are the 4 steps to using the box method. First, rewrite the function, boxing all the variables that are treated as constants. This includes any exponents or natural logs that are attached to the variables that are being treated as constants. The second step is taking the derivative of each piece outside of those boxes. The third step, multiply those boxes back in. And the fourth, simplify the expression. Recall that the function that we've been working with has two partial derivatives, one with respect to x and one with respect to y. We figured out that the partial derivative with respect to x was 6xy plus 3, but what about the partial derivative with respect to y? Remember that now y will be the variable and x will be treated as a constant, so all the x's should be in boxes. Pause this video and use the 4 steps of the box method to get the partial derivative of f with respect to y. And then in a few moments, I'll show you the answer so you can check your work. Here's the solution to the partial derivative of f with respect to y. Notice that in the first step, I rearranged the boxes so that they were at the end of each piece. You don't need to do this necessarily, but it can make taking the derivative easier because you see the 3 and the y together. Check your progress against this solution. Note that you don't always have to go through each of these 4 steps separately. As you get better at partial derivatives, you may find yourself combining steps, but doing each step separately, particularly when you're first learning, helps minimize errors. Finally, here are a few practice problems to practice with on your own. I've also included a challenge question that uses the natural log. If you already know how to take the derivative of the natural log in regular derivatives, partial derivatives aren't much harder with the box method. If you're struggling with using natural logs within partial derivatives, I've created a separate video to show you how to combine these two topics successfully. Thanks for watching.